I just watched a recent episode of Numberphile. It's talking about the base Fibonacci, and there's a Tony's trick. Is sort of party trick, and he talks about how to use Zeckendorf decomposition to do this. I'm not going to cover the math part. You can just watch this video. It's quite comprehensive, and I just want to show you how to do this in Wolfram Language. So in this case, let's just check one of the examples in the video. It's 72. So rows 1, 3, 6, 9 are checked, and you can recover this number directly using the sum of Fibonacci. And this is the same thing we have here. And I think he was talking about the 72 here.
It's got a 7 in it and a 2 in it. Is it 72?
Yes. Okay. So this is exactly the result in this video, and I'm going to show you two ways to create it, this type of table. One is the version that follows the video is about Zeckendorf representation.
Yes, add into the decomposition. So that's 21 plus 5 plus 1, right?
1, 4, 7 are checked. Okay, this is also correct from his computation and agree with our app. So there are a couple of functions that you can directly using in Wolfram Language. The function repository is a nice open source extension to the core functions. So if you check Zeckendorf representation on the website, there should be two functions available. One is a dual Zeckendorf and the Zeckendorf itself. Okay, also related to Fibonacci stuff. Okay, let's start with the Zeckendorf one. So to use this function is quite simple. You just type a resource function in the notebook, and also you want to read the details and options here, because the Fibonacci number used both in this function and in the original video are shifted version. So it started from 1, 2 instead of from 1, 1. So if it started from 1, 1, then the representation would not be unique. So it's the same thing here. We start using resource function Zeckendorf representation to first 100 integers. So this is what we have is 1, 1, 0, 1, 0, 0, 1, 0, 1, and 1, 0. So in this case, you can tell that all numbers, the first one here is the highest position, and this is the lowest position. So to make it easy for me to program, I actually use this function. It's called the pad left. So what the pad left does is it adds number of zeros to the left-hand side of the, I would say maybe this is the first one in the list or last, which really depends on which way you start to count. So that in this final representation, all numbers are of the same length. The next step is also I want to just make it easy for my code in the below. So there is a conversion. It's sort of like you go from binary to decimal. So in this case, it's from Fibonacci-base to decimal. So the idea is really simple. Say you have a number 1, 2, 3 in decimal. So it should be 1, 2, 3, a list of a number dot product, 10 to the power of 0, 10 to the power of 1, and 10 to the power of 2. Sorry, the reverse should be 0 here. And so this is the same thing as this list of numbers. So it's the same thing for the base conversion and from the largest number to the lowest number. And you can test this number conversion base for some of the selected numbers inside the list here. So what we do here is you treat all the numbers that satisfy this in this block, and only choose the number that contains the lowest, contains 1 at the lowest decimal point. So it's from -1 because in this convention, the lowest number is on the right-hand side. So it basically checks all the entries with the 1 at the end, or the rightmost position. And what we have is actually a large matrix. Okay, and then if you want to convert each guy back into decimal position, you simply do matrix product. So it's all inner product. And what's the consequence of containing the number 1 at the rightmost position is, well, according to convention here, 1, 2, 3, 4, 5. So if we have 1 at position 1, here it's basically like the -1 here. If it's 2, it should be like -2. And this number will be in the first row. So you can see this number 1, 4, 6, 9, 12, and something. This is numbers in the first row. And the same thing happens if we switch -1 to -2 here. So 2, 7, 10, 15, 20. So these are the number with 1 at the second position from right. Say, for example, 2, this is first, the second one, it contains 1 at the second position from right. 1, 2, 3, 4, 5, 6, 7. For 7, it's limitless because it has 1 on the second item from right. So this matches the 2, 7, and you can just manually check these numbers satisfy this condition. And 2, 7, 10, 15, 20, 2, 7, 10, 15, 20, 23, and so on. These are number in the second row. Okay, so this applies to all the rows, and the easy way to do that is using table and vary the k here. It's from 1 to ml, and the maximum length of the items in the block here. So, and once we have this variable, store the data here, we simply put it here and map an association to the elements in the list. So for each row, I highlight the head. It is because it's a Fibonacci number, it really plays a key role in debunk this party trick. And if I have a number checked, and I just put an orange check here, if it's 1, or it's my number is in the list, so you definitely will have a check here. One thing to notice is because, for example, this number has 1 at several places, so definitely lots of number will be duplicated. If you want to check the duplications of numbers, what you can do is say just get this result, and let's just flatten it. Okay, and let's do a tally. Then you can check the occurrence of each number in different rows. So some occurs, say 80 will occur 4 times, and 1 is definitely just occur once. So this is also a very interesting result you can check with the average number of sort of like digits, non-zero digits in Zeckendorf representations. This is usually you can just check on OEIS, and I'll show you one of the link in the next example. And once you have the tabular formed, and you give it some options to fix its size, and then I can just wrap everything inside the manipulate and change the input and shows how the check mark is associated with the non-zero digits in expansions. All right, this concludes the first part, and then let's move to the second one. It's called dual Zeckendorf representation. It's code-wise, it's almost the same as the first one. What's the difference is this function. So you can just hover mouse over there and click the book sign, and it brings you to the definition. And I have some details for you to read. And it used the same idea of a shifted Fibonacci numbers. It's from 1, 2 instead of 1, 1. And this function uses a lazy algorithm instead of a greedy algorithm. So this one is implemented with exactly the same idea that's displaced on OEIS. And if you want to check that, just click the source notebook button, or you go back to the notebook. Let's hover the mouse over this guy, and there's another book sign here. You click it, it will open the local definition for you. You can read all the source code behind it. And this function actually works quite well. It's quite fast. As the Zeckendorf version, you click the function and hit Shift Enter, so it will give you a list of representations. You can also go back to this notebook, this documentation page for that, and it shows you the dual Zeckendorf representation for numbers from 1 to 20. So the key here, or the key difference between this one and the Zeckendorf version is that in the Zeckendorf version, you are not allowed to have 1, 1. So say if you go back to the expression here, this for the original Zeckendorf, so 1 must be sort of isolated with each other. So you either have a bunch of 0, or like occasionally you have 1 in the list, but you never have 1, 1 in the list. It's very similar idea in this expression. You just notice you can have 1, 1 here, but you are not allowed to have 0, 0 here. So you can check. Definitely there is no 0, 0. But it's fine to have some leading zeros because after we pad, definitely allowed we have zeros to the left-hand side of the elements. So, but for the first one here, and you no longer allowed to have consecutive zeros here. Okay, so these are just padding zeros. The same idea just used in the first example. And now we need another base. The reason the algorithm is the same, but using the dual Zeckendorf and the Zeckendorf, they definitely represent the same number, but each number will have probably different length in the representation. So in the first example, for a number from 1 to 100, the maximum length of sort of bits is 10. But in our case, it's just 9. So I need to recreate a different set of base. So it simply drop the first one from the list above. And this basically tests my algorithm on the same numbers, same ideas. So in this case, you can see if I want to choose the number with 1 at the end, there are way more numbers than it used to be. And then I called DZR, the dual Zeckendorf representation, to store my final result that I'll be using for our tabulate. And then we can do the same thing for check the tally, but in this time, I no longer check the number of the representation only. I can also check the length of each element. So some of the length is really large, and some are really small. And I can also just quickly do this, flatten. because each length seems to be unique, I can just leave it like this. And this number checks the occurrence of each element. So for 100, it occurs 7 times. 77 occurs like 6 times. Similarly, 1 only occurs like 1 time. Okay. So this is a sort of the idea that we can do very simple statistics for that. And there is a closed form for the average number of ones in the dual Zeckendorf expression. It's included in the documentation for this function. So let's just click that again. And if you scroll down, there are neat examples here. I think it shows you the closed form for average density of ones in the k-bit dual Zeckendorf representations. So you can just read this part and also go back to the OEIS, the link I have here, so you can check the actual citation on maybe the first guy that derived this equation from that website. Okay, so let's do the same thing here to create the tabular. You can just ignore this part. Okay, ignore this part. Okay, use manipulate, and almost the same code, except I have a little bit formatting code here because some of the lists are really long. So I have to break it down into 2 lines for it to properly fit into my recording window here. So it's quite similar to the example above. You can scroll or just drag the slider around, and you can see, except for some of the leading missing lines can be neighboring to each other, you are not allowed to have consecutive missing lines for the lowest V and everything above. Okay, so this is the same observation we have to check the arrays. And let's see if we have number 49 here. This is a dynamic expression which is synced with the slide above. For example, I go 46 or 47, say. So it's a number sum of 2, 3, 8, 12, 13, and 21. So I can just replace this number in the list. Check it. It's 47. It's perfect. It's the correct. Okay, so this is a conclusion about Zeckendorf and the dual Zeckendorf, and the absolute amazing video on Numberphile about this interesting party trick. Okay, so hopefully you learned something, and let's see you next time for more interesting videos and more interesting companion notebooks for Numberphile videos. Bye-bye.